When we get started, so we're very happy to have Cuesta-Lazaro here to tell us about generative modeling, go from no experience to fusion models. So thank you, Carol, for agreeing to do this.
Thank you. Yeah, so the hope today is to take you from wherever you are. So maybe you don't know anything about machine learning, maybe you know a little bit, to building your first generative model, hopefully. So we'll be using JAX for this tools. If you're not familiar with it, in theory, we should also try to build from the ground up, but obviously feel free to ask any questions. But first, I wanted to start by giving you some background on what we're going to cover. And in particular, yeah, what do I mean by generative models and why do I think they're useful for science? So yesterday in the talk, I was showing some examples of awesome generative models. So some of my favorite ones. In particular, there's this Generative, Generative model that generates playable worlds given a text prompt. Right? So this very high dimensional inference problem where you're trying to generate a playable world, so where a player can actually control one of the players and generate this like huge diversity of worlds. So these images are like 1,000 squared times time, right? Because it's a video, so extremely high dimensional, and you can still control it with text. So it's really, really impressive. There's some really cool examples from the sciences as well, in particular from chemistry, in the area of drug discovery. So we're trying to generate drugs that have a particular property that we want to cure any disease. And we can build generative models that build those drugs. And then we can even build automated wet labs that will test whether that drug actually fulfills the property or not. So whether the generative model was right or not, and build a feedback loop on top. So these are becoming extremely useful in all areas of science. Now, one of the reasons why they become so useful is because we've been able to grow them up, right? And there's this very cute example from Google where they tried to train a generative model that was very, very small and grow it out to see what happened, right? So here the prompt was to build, to draw a portrait of a kangaroo wearing an orange hoodie, blue sunglasses, standing on the grass in front of the Sydney Opera House, holding a sign on the chair that says, "Welcome, friends." So this is the tiniest model they built. Not too bad, right? I guess all the elements are kind of there, but you can tell they're not quite right, right? In particular, the text is really, really poor, but all the elements as well, they all kind of fail. If you build a slightly larger model, so it's going from 350 million parameters to 750 million parameters, it's starting to get a bit better, right? The quality of the generation is definitely better, but the prompt is not that well fulfilled, let's say, right? So the text is still very poor. If you build an even larger model, so 3 billion parameters instead, now it's getting very, very close, right? So now maybe you can recognize the Sydney Opera House as something that looks like it, a fractal of it maybe. And the text is getting closer. It's not quite there, but it's getting very close. If you go to an even larger model, 20 billion parameters, then things are starting to look really actually very, very good. So you can clearly see the effect of model size. And why things have become so good in the past few years is because we've actually been able to train these models at scale. So make them very, very large and train them on large data sets as well. So here we're only changing the size of the model, but obviously you could do similar plots with the data set size. And that's not the only advancement, right? We've also seen models go from highly specialized models that could only do one thing, like AlphaGo. I'm sure many of you remember the documentary where the first time an AI actually defeated the best human at Go. But that AI was awesome at Go, but it couldn't do anything else. Whereas the best human at Go can still function in daily life, right? That's not something AlphaGo could do. However, now we have AIs that can actually do plenty of things, right? So yeah, you have different tasks and different particular tests, testing the knowledge from law to chemistry to physics, and AIs are actually doing really well all across the board, right? So we're getting closer to this idea of artificial general intelligence. So AIs that can actually do many, many things. And the core of this is generative modeling. That's what we're going to be talking about today. In this kind of generative models, we've also seen this scaling laws, right? So the same idea I was talking about earlier. So you can see the test loss, so how well the model is doing on a test set on the y-axis. On the x-axis, you have the data set size. So how large was your training set for training? So this is for text in particular. But again, you can make many similar plots for any modality, right? It could be images, it could be text, it could be anything. And you see this exponential trends, right? Where as you grow your data set, models become better and better. And so far, we haven't seen this plateau, right? So it's very exciting because it means with current technology, with current models, and data sets, if we keep scaling, things will getting better and better. Obviously, this might plateau at some point, but it looks like we're not there yet. Same with the number of parameters, right? So again, this is growing the model, and growing the data leads to better models. Some interesting things that people have been finding as well is this idea of emergent abilities. So if you measure the capacity of the language model to do some tasks, like on the first box there, we have modulus arithmetic. So how well can the model do modulus arithmetic during training? So on the x-axis, you have training steps. So how many times do you train your model? On the y-axis, you have accuracy. And what you see is that the model at first is terrible, right? And then you see kind of a phase transition where the model actually becomes good at different things. Actually, you can see many of these skills seem to peak at the same time, right? So it looks like models are pretty terrible. You have a phase transition, they get very good at something. So that's kind of scary, right? Because you'll never know when they'll actually develop a new ability. But from the perspective of training dynamics, is very interesting, right? How do models become good at things is still one of the open questions. But obviously, we've seen them do very interesting things, right? So with text, you can do things like ask ChatGPT to draw a unicorn in Pixie. So if you use, I don't know, Pixie, I don't know how people call it, but if you try to use it on LaTeX, it's actually really hard, right? If you try to draw any diagram with Pixie, it's really, really painful. So this is an example where people asked ChatGPT to draw a unicorn in Pixie, and well, it did something, right? It's not too bad. So this was at the beginning of training. But it looks more like a pig than a unicorn, I would say, right? Later in training, it was getting a bit closer, right? Removing some of the pig features and turning more into a unicorn. And by the end of training, it was actually doing something pretty decent, right? So it means it seems to have some visual understanding of the world as well, even though this model in particular was only trained on text, which is very, very impressive. Another example in a similar vein is the model was asked to generate code in JavaScript that will create images that will look like a painting of Kandinsky. And this is one example from a true painting of Kandinsky. This is what the model did at the beginning of training. So actually, if you look at some early Kandinsky, it's not too bad. But this is the kind of things the models do at the end of training, right? So they seem to really get an understanding of what Kandinsky shapes tend to look like and be able to generate them through code, which is really super impressive. Okay, so these are some examples just to motivate why actually learning what generative modeling is just an interesting thing to do per se, apart from the fact that it's very useful in science. But what we're going to do today is on the first part of this tutorial, we're going to start with the building blocks of machine learning. So understanding what a basic machine learning problem looks like, and building a first classifier. So this is a very simple example where we will be given numbers and we'll build our first classifier using JAX. So this is the first tutorial. Then we'll have a break in between before we move into an introduction of generative models and do a tutorial on that. Now, feel free to ask questions at any time. I think it'd be better to make it as interactive as possible. So yeah, just raise your hand and ask any question you might have as we go. But yeah, we're going to start with just from the very basic, the building blocks of machine learning. Does everything make sense? Yeah, we're all happy. So first, we're going to talk about the most basic thing, data, right? So that's the first thing we need. And in particular, we need to think carefully about what are the symmetries in our data sets that we can take advantage of when we build machine learning models. So this is going to be a theme throughout. So here you have 3 examples of very different data modalities. On one hand, you have point clouds, for instance. This is an example from galaxy clustering, where each point here is a galaxy, DESI in particular. You can have images, so pixelized, right? So n by n matrices that define an image. Or you can have something like text, right? Which is more unstructured in a way, right? So you only have sequences or sets. So these are some examples of data modality. Now, the issue is that when we go to high dimensional, so for instance, here you have an image that is 1,000 squared, it's very, very hard for any data set to actually cover all possible dimension combinations, right? So this is what people refer to as the curse of dimensionality. So you put this on a very simplified diagram, Going in 2D, you can very easily cover all the dimensions with only like, what, 9 points there, right? If you grow this into higher dimensions, it becomes really, really hard to cover the space, right? Volume is growing too quickly for your data to actually catch up. So how come can we build models for images that are 1,000 square dimensions? That sounds really tricky, right? And the idea is that data sets don't actually live in a 1,000 squared manifold. The manifold is actually smaller, but we don't know what it actually is, right? But what we can do is take advantage of some things we know about the data modality. So this is what people refer to as inductive biases. So things we know about the underlying data modality that we can take advantage of. And in particular, symmetries are a big one. So if you think about all the possible machine learning architectures, one way to categorize them is according to their symmetry. So this is an example from a very nice review on geometric deep learning that I highly recommend if you're interested in learning more about machine learning architectures. But all these different models that you might have heard of, like CNNs, like convolutional neural network, GNNs, graph neural networks, deep sets, transformers, you can classify them according to the symmetries that they're actually trying to preserve. So that's what we're going to talk about now. So what architecture is actually linked to what symmetry. And this is helpful because those symmetries will actually make the manifold where the data lives much smaller than it actually is, right? From 1,000 squared to something much smaller, and actually make the problem practical. That's why we don't use the same architecture for any data set, because it actually won't scale to your higher dimensionality data sets. Actually, in these tutorials, we're only going to use one architecture, which is the simplest one, the multi-layer perceptron. But I want you to be aware of the fact that all these different architectures exist for a reason. If you try this multi-layer perceptron on a higher dimensionality data set, it will just not work. Okay, so what is the most basic architecture? We don't put any inductive biases in. So we're not accounting for any symmetries here. Well, this is a multi-layer perceptron. So here you have an input layer. So you have some input. In our classifier example, we're going to have a very low resolution image. So I think it's 64 square pixels or something like that, with zeros and ones. So it's going to be a number. And we're going to do is we're going to have the value of each pixel as what's one input in our neural network. What we want is to get an output layer that will give us a classification accuracy for each number. So here we will want to know that this is a 4. But the idea is what's happening in these arrows and neurons, so this point here is what we call a neuron. What's happening is that we're just learning some weights that will combine the inputs. So if you look at any layer, what's happening here is you'll have some inputs to your layer. So in the first layer, those inputs will actually be the pixel values, right? So we'll take all the pixel values and just weight them. So we'll do like a weighted sum of all the pixel values. And those weights are the parameters that we're trying to fit or learn, right? Then we'll add some biases. So that is a weighted sum plus some value. And then we'll pass them through a nonlinearity. So that nonlinearity is pretty arbitrary. It could be anything that is nonlinear. So people usually do preludes, which means just do something like this, like a very step-like looking thing. But it could be anything. The idea is that we assume there's a nonlinear relation between our output and our input. So if we only did this, we can only learn linear relations, right? If we want to learn something nonlinear, we have to add it in. So the basic building blocks are very simple, right? You're taking linear, like weighted sum combinations of your inputs, and you're passing them through. So very, very simple. So each of these layers will have a set of 3 weights that we want to adjust according to our loss function that we'll talk about later. But here we're not making any assumptions about the underlying data manifold, right? There's no asymmetries, there's nothing here. So it's very data agnostic, but it doesn't scale well with a number of dimensions. If you had something like an image, for instance, in images, usually we're interested in features that are translation invariant. So let's say that we want to find a cat. We don't care if the cat is in the upper bit of image or in the lower bit, right? Whatever is finding cats should work equally well, regardless of where the cat is. Right? So usually, convolutional networks kind of exploit the fact that we want translation invariant features in our architectures. So the way they work is actually very simple. So you're gonna build a filter
In this case, it's a 3x3 filter. So if the blue squares are your image, your original pixelized image, you're going to slide a filter of unknown weights. So these are the weights you're trying to learn, the values in the filter. And you will just slide the same filter throughout the image. So this is kind of the features that you're trying to learn, whatever the filter is doing on the image. But you're using the same filter in every location of the image. You're not learning different filters for different locations. Which, if we're looking at it like a multi-layer perceptron, I showed you earlier, will learn different features with different locations. Whereas here, you're just sliding the same filter. So it's very useful when you're looking for the same features, regardless of translation. So. Another data representation that has symmetries is sets, right? So let's say that I want to learn how to add numbers. So if I change the order of my inputs, I don't want my output to change, right? My output should be invariant to permutations of the inputs. Now, in multi-layer perceptron, that won't be true. If I change the order of my inputs, the results might actually probably change. It might approximately be true, but it doesn't have to be true, right? It's not, the architecture is not enforcing this symmetry that we know is actually there. So what we can do is something very simple. So what we want is a function of our input. So if X is our input, our set that we're inputting, we want a function that is permutation invariant, right? So regardless of the permutation of X, I get the same input. And one way to actually achieve that is we pass each input independently through a neural network, a multi-layer perceptron, and then we aggregate them in a permutation invariant way by taking a sum, a mean, and max, any function that is actually permutation invariant. These architectures are actually very simple, but they enforce this permutation invariance by treating the inputs as independent and then combining them in permutation invariant ways. Now, you might have heard about transformers. So transformers have become kind of the unifying architecture, so you can use them actually for many different data set types. So from text to images now with vision transformers, or to any input whatsoever. And it's interesting because they actually do have an inductive bias as well, which is permutation invariant, same as deep sets. But actually, when we look at images or text, we don't want it to be permutation invariant. So we'll discuss a bit more about this, but the reason why people like transformers is not so much for the inductive bias, but because they scale very well. So it looks like we can make really large models and still train them, which is not true for other architectures. If you grow a CNN at some point, your loss won't get better. Whereas with transformers, that seems to be the case, that they can scale better than other architectures. And how they work is actually quite interesting. So the basic mechanism is called the attention mechanism, which is based on this idea of queries, keys, and values. So this might seem a bit abstract at first, but the idea is that you have some input, what we call a token, but it's just an input unit. So in text, it can be a word, right? That could be a token. So you have a word input or whatever it is, it could be a patch in an image. We call this X. And we're going to compute what we call a query, a key, and a value. So these are matrices that we're learning that once applied to X will give us the query vector, the key vector, and the value vector. And these have different meanings. So the query is asking the question, what is X looking for? What is our token looking for? Whereas the key is what does the token actually contain? And the value is what it provides. So this might seem very abstract, but let's look at one example. So if you have a sentence like this, the dog chased the cat because it was playful, and you want to understand what is it referring to, right? So in this case, for instance, you will want to have, so if it is your query, my question is, what is it referring to? That's the query. Well, it's referring to dog, right? So what I will want is that the key for dog, once I take the dot product between my query and my key, I would want that to have a high value. So this is what the attention mechanism is doing here. So it's finding pairs of keys and values that have, of queries and keys that have a strong correspondence, right? So when you take a dot product, that will be high. And then you will copy the value of dog into it, right? So this is what we call attending to, because it means that this token is really attending to the content of this token. So you can build this like long range correlations between tokens, which otherwise will be lost, right? So you don't want it to only know about what's nearby. If you thought about a convolutional model, you will take convolutions on the small filters. So it will only know about what's happening nearby. But this attention mechanism allows us to pay attention to things that might be very far away. And it is because you've learned ways to query and retrieve. So this is kind of a retrieval system that allows you to pay attention to different things. So this is the basic mechanism. Now, it is permutation invariant, right? Because if I move things around, if my queries and keys and values are the same, I'll get the same output. But we don't necessarily want it to be permutation invariant, right? So if we have this two sentence, dog bites man, man bites dog, they don't have the same meaning, right? So we don't necessarily want our transformer to be permutation invariant. So people usually break this symmetry by adding what we call possessional encodings. So we add an extra value to each word that tells it, am I first, am I second, or am I third, right? So it's a bit interesting because usually we talk about inductive biases or symmetries as something very desirable. But you know the symmetries of your data set, you put them in. But transformers actually came the other way around. We're like, okay, we have an architecture that has this symmetry, but we don't actually want the symmetry. How do we break it? So it doesn't seem quite right. So I don't think it'll be the definitive architecture, right? Seems very coincidental, but it's an interesting fact. And yeah, that's good. Okay, beyond architecture, so we've talked about these, I think, 4 different architectures, right? Multi-layer perceptrons, big sets, transformers, and convolutional neural networks. So these are amongst the most typical architectures because they cover most of the data types. Now, a very important building block is the loss function. Right? So we have all these free parameters. How do we adjust them? So how do we find the set of free parameters that work well for our problem? So for that, we need to define what working well means. And this is what the loss function is doing, right? It's telling the model what a mistake looks like and what the right answer looks like. So if you're working on a regression problem, you're trying to predict, I don't know, the age of the person, then you could use a mean square error, right? We'll talk a bit more about what a classification loss looks like. But I first wanted to show you kind of what the loss might look like, or what the loss landscape might look like. Because when you picture a loss, I think you picture something like this, right? So if I have 3 parameters that I'm trying to optimize, right? So each dimension here is 1 parameter. You imagine something that is very smooth and convex, right? So you have 1 minimum and you can like smoothly fall into it, right? That's what I will naively picture as a loss, something that's very complex. So I can find, so that this means that all these models are bad. This model is very good. But there's a very clear distinction between the bad models that have a large loss and the good model that has a very low loss, right? Now, what losses actually tend to look like is something more like this, right? So people have found like interesting ways of visualizing them. And this is how a loss function might actually look like. So it's more, actually it looks a bit like Arizona, right? Like Tucson around us. This was, yeah. Looks like mountains or valleys, etc. So here it still looks like you have a global minimum. This is just because of the way the visualization looks like. Actually, you don't necessarily have something like this, right? But you have loads of local minima and maxima as well, right? So it's a much trickier landscape than the one here, right? That's why optimization algorithms are actually important as well. If the optimization problem was simple, most algorithms would be able to find the minimum. But if you have this like minefield, it's much harder, right? First of all, because you can get stuck into a local minima, which we always get stuck in local minima. You never try to find the global minima, so we'll never try to find this because it's too hard, very high dimensions. And the thing is that sometimes being here is good enough, right? We just want a good enough model. We don't want to find the best model necessarily, because that might be impossible, right? So oftentimes we're just happy with one of these values. But I just wanted to show you how the loss landscape actually tends to look like. So that you're aware of it at least. Right, so this means we have to care about how we optimize our models as well, right? So usually what we do is do gradient descent. So this is our loss function. So right, so it is moving now. So if you start from one point, right? And these are your free parameters that you want to optimize over, and that's the value of your loss. Different optimizers would be like first order, second order, right? So are you only using the derivative of the first derivative of the loss? Are you using the first and the second derivatives? Are you using the history, right? So some of these optimizers will forget about what happened before. Some of them will carry what we call momentum, meaning they'll have some memory about the trajectory they took, right? So that you're not completely taken off track by one iteration, right? So that you can stay on the same path. But the reason why we have so many different optimizers is because it's not a simple problem, right? But for now, we're going to be working with the simplest one. So it doesn't really matter, right, for the simplest problems. But you can find problems where actually the optimizer can make a big difference when the loss is very tricky to optimize. Maga, look, what we're going to be doing in this first tutorial is to learn to classify. So we're going to have images of numbers, and what we want to output is a probability of a number being whatever, right? So for instance, here, we want to know, well, this is clearly an 8, so it should have high probability. But actually, some of these can be tricky, right? So this is probably, I don't know, I would say a 2. But I mean, it could be a 0, right, if you draw it quickly, or it could be a 6 if you turn it around. So you probably don't want a model that just says, oh, this is for sure a 2. You want a model that can capture the uncertainty on that, on that too. Same for the others, right? So that's why we care about models that can output probability values, because obviously things are not black or white. Okay, so the question is, how do we output a probability value for these numbers, right? So one thing we can do is to have an output per class, right? So what we want to do is to output a probability value per class from 0 to 10, right? Or to 9, yeah. So we have 10 possible outputs. Now, for probability distributions, obviously, we want the value to be between 0 and 1 for each individual probability. And we also want it to be normalized, right? So we want them to adapt to 1. So a very simple way in which we can do that is by using the softmax transformation. So we're going to, for each output, we're going to make sure that we squeeze them into the 0 and 1 range and that they add up to 1, right? So you pass this for your output and you make sure that everything is well defined. Okay, so we have a way to getting inputs all the way to things that could represent probability values. But what is the loss function? So what do we how do we tell the model what is a good model and what isn't? So the question we're asking here is, how different are two probability distributions? So if I give you a model prediction that looks like this, right? So I randomly initialize my model, and it gives me this probability distribution for each class. And the truth is 0. How different are these two probability distributions is what we want to use to penalize the model. So you can use what we call the KL divergence, which is the measure of how different two distributions are. And if you write it down for a discrete problem, it actually looks very simple. So it's just the log probability of your class prediction times the actual class. So if you go through this, you can convince yourself, so if the true class is 0, and you give it a high probability, the loss will be low, whereas if you get the wrong one, the more wrong you are, the higher will be the loss, right? Which is what you want for the correct loss function. Right, so that would be the predicted probability, and you have the true class. So we're going to be using this as our loss function. Where, yeah, with y is 1, if the true class is that 1, or it is 0 otherwise. So we're going to be building this in JAX. So for machine learning, there's basically right now 2 major frameworks. So you have PyTorch, you might have heard of, and you have JAX. Now, PyTorch is probably the most popular one, the one that most people use. But I think JAX has many advantages that transfer to more generic science problems. So I use JAX not only for machine learning, but for many other science problems I work on. So I think it's useful for people to learn JAX. And also, it really exposes how the model actually works. Like, there isn't as much like wrappers around it. Like PyTorch, you could train a model without knowing what you're doing at all. Whereas in JAX, that's way more challenging. maybe you could manage, but I think you will struggle to not understand what's happening and get it to work. So that's why I think for these kind of tutorials, using JAX is actually probably better, especially if you don't know any PyTorch. Starting with JAX, I think, is probably a better idea to really understand what you're doing. So I have written some like boilerplate code in JAX. So you have some class for your architecture, right? So where you define what input to output looks like. So here, this is a multi-layer perceptron. So dense is just this linear combination of weights and features. So you can see, once you're working on it, you can see what the shapes of each pass look like, right? So how the shape is changing. Then silo is just a type of nonlinearity, but you can use any other nonlinearity. The idea is that you're returning an output of whatever size you need. In this case, I think I'm returning something of size 2. Then JAX very clearly separates the architecture from the model parameters, which is not something that PyTorch does. And the idea is that you will first initialize, so you will call your model and initialize the parameters at random first. So you control the parameter initialization from the beginning. So these are the weights of your neural network. And then you have some way of calling the model. So you will apply the parameters to your model together with an input, and you'll get an output, right? So there's a very clean separation between the architecture, the parameters, and how you call it. Okay, so with that, we can start with the first tutorial. So I don't know if you all have access to the GitHub repo. I think it was sent around, but otherwise I'll also put up here. So I've used search for Floppy, my username. It's called From Zero to Generative JAX tutorial. But I think it was sent around with the announcement, so you should be able to find it on the email as well. So this is the first tutorial, build a classifier. You can open it directly in Colab, so you can click this link here. This is Google Colab, so it's a platform Google has to do computation online. And you can choose to use a GPU. So I think you can change here to a GPU. Now I ran out of free credits, so I can't do it actually, but you guys should be able to. Now for this problem, you don't actually need the GPUs, so don't use it. Like you can do everything on CPUs because it's actually pretty small scale. But you'll install all the libraries you need, etc., so that you can actually start running the tutorial. So you see that there are to-dos around. So you find things that say to do. So this is the stuff that you can fill out yourself. Now, if you have any problems, obviously let me know. But if you're really, really stuck and I'm not around, then you can go to the solutions branch and find a solution as well. But I would really recommend trying to do it yourself first, obviously. So yeah, let's say we can take the next half an hour to work on this tutorial. So at 2:40, we can come back, then take a bit of break and get into the second part on generative models. But yeah, if you have any questions, just raise your hand. Well, maybe now's a good time if you have any general questions about anything I explained, so feel free to ask.
So if you're stuck with, you raise your hand. So then we can.
Did anyone get stuck at building the model and initializing the parameters, or is that clear? No measure issues. But has anyone gotten to building the MLP or not quite yet? Yeah.
Actually, I got stuck when I expected shape. I'm not exactly sure what to put there.
Right. So, so this is just flattening your data, right? So you go from your 64 image to use a flat array. And now the idea is that you build the architecture on top, right?
Oh, I think
Oh, yeah.
this question was about
Yeah,
the
it's one of
intent.
yeah, it's intent.
Oh, I'm sorry. Yeah.
Yeah.
Oh, right. So you just what shape do you expect it to have?
I mean, I tried numbers and I tried words. I'm not exactly sure what.
Oh yeah, numbers. Like it should be a tuple with the shapes. Like a tuple with like an array with a shape.
Oh, okay. And how many digits? Like 28?
Well, there should be 3 numbers here.
So 2 layers.
Yeah, whatever number you prefer. There's something you can experiment with, right? To see what happens when you add more.
I actually got 4 numbers. in my-
Right, there may be 4. There may
Yeah,
be 4.
Might be 4.
The channels.
Yeah, so there might be a 1 at the end.
Yeah.
There should be 3 numbers that are not 1, and then 1.
Can you go over the one you were originally talking about, the building block 2? What do we put in there? What are we looking for?
Right, so this is the actual architecture of the model, right? So we'll be using the most basic one I explained, which is a multi-layer perceptron. And so I had right, okay. Oh, what's that? Oops. Yeah, what's going on with this? Right. So here you have an example of how those architectures look like, right? So this is a linear layer. So this is doing the weight multiplication linearly, right? So this will be adding the linear layer. This will add a nonlinearity, right? And here I'm adding 2 of them, but you can add as many as you want. So you can have a 3-layer, 4-layer, whatever you want. But this is kind of how JAX does it. So dense would be in a linear layer. It says dense because it's kind of fully connected. The arrows are all connected that I had in the original architecture, right? So if we go back, well, actually here, you can see that this point is pointing to all other neurons. So that's why it's called dense. But it's just a linear matrix multiplication, right? And then we add the nonlinearity.
The 64 arbitrary.
Yes, completely arbitrary.
So even the last feature equals 2 is arbitrary.
Right, so actually the last one is not arbitrary, right? Because this is going to be the shape of your output. So here, if you want to do a binary classification, well, actually you only need 1 output. So this would be if you want to output 2 things. Now, because we're trying to classify the numbers from 0 to 9, we want 10 outputs, right? Because we want the probability of each individual class. But the other numbers are actually arbitrary. So these are what we call hyperparameters, which are numbers that could have many different values. Some of them will be better than others, and the only thing you can do is try. One day we might have a theory of deep learning and we might be able to predict what those values should be, but so far no one has been very successful at that.
Any other questions or anything else people are stuck with?
Alexis, did that answer your question?
Yes, thank
Okay.
you.
Does the shape look sensible now or
Close enough.
no?
Sorry.
I actually, honestly.
No, I was just trying to get it.
Right. So you want to. Right.
Yeah, sure.
So when I have a couple, you want to, there's gonna be multi-dimensional. So. This is different.
Oh, yeah, yeah. Yeah.
Right. So this is a tablet, right? And now I can have different dimensions. There's 4 dimensions, right?
Okay.
I want you to guess what you think the first dimension should be, the second, the third. So you can have an array or a tuple.
Oh,
Or
okay.
or an array.
Right.
So,
And I should.
no, that won't work. So this is. Right. So, okay, so. Batch is how many examples you want to get in one problem, right?
Yeah.
So you're gonna get 64 examples
Right.
of images. So now, the images have a certain dimensionality.
Yeah, that's just one. Basically.
So the shape is probably only something like the number of examples you can take. The dimensionality. Like,
Yes.
number of examples. We get 64 examples.
Okay.
And this is the dimensions of the array.
Yeah.
Now, this is one because you have one tab. Like, you can have color images, you have RGB.
Yeah.
Then it doesn't only have one tab.
Okay.
It's that one.
And I would, yes.
You would have to have guessed this. Like.
Oh, okay.
Yeah.
Oh, no, I get it. Okay, so.
Yeah, I think the question wasn't very well posed.
No, no, I
Right.
can't. So I just think of it.
Right,
But
exactly.
not always NumPy at the end of the day is compiled into.
Oh, so you basically.
But I think the chances like optimal.
Right, so like, so you understand with that.
Whereas
Right,
NumPy.
so you're not using one example at a time, because if you.
In this case, it's not.
Okay.
Yeah, it doesn't have.
And then you basically.
Surprisingly,
Sounds like.
Exactly.
Okay.
Exactly, so
I think
you're
that-
using, yeah, right,
Yeah.
Right.
That's why Jax has this NumPy for modules.
Which is how many examples do I get?
Right.
Just make my boss.
Sure, code is pure.
Right.
Thank you very much.
Chances of just in time, that's right.
Wondering, so
You can
for example, the diffusion,
Yeah, like number.
the model can predict the galaxy distribution also kind of small box. I'm wondering if it's also possible to predict the loss landscape you just showed. Like, if I only got a slice of the loss landscape, can something like loss landscape also.
Yeah.
Right, it doesn't have to be really hard, but it's very non-linear problem, right? So it's actually really
So it
hard.
says I have
Yeah.
to write
But
down.
people
the
do try to
logs of
predict how well,
class function.
given all the neural networks we've trained in the
So it's
past.
really.
It's this
Five sample run.
But I don't know
How well
what-
will it perform without having to run the training, right?
I
Is that
don't know if
predictable?
that is.
And some cases seems to
not.
be,
Yeah,
which is
so,
interesting, right?
it would be ZI.
Right, if you've trained enough neural networks,
Then there's this
yeah, the model has
expectation.
some intuition on what will actually be good, which ones will be bad.
Exponentiation doesn't-
But we don't
I don't know, like,
understand
what is-
theoretically why this is the case. So that's all
Oh,
we're
yeah,
missing,
so
right? It's all very empirical.
It's like-
If I change those and it stops working. Why? I don't know.
Outputs could be like lazy numbers.
Yeah, but these are very interesting questions.
If you think the exponential of
So
that,
when you're
you're
comparing
gonna get something. which
models,
also is the-
performance
Yeah.
is different, different model.
So that's why everything
parameters
gets
set.
shifted.
Right, or
Does
So
that
that whatever the
means
maximum
that
is, it
however
gets
you
scaled
add
down to zero.
parameters to the model,
Um,
you
then
decrease the loss, or you
You
need
take
to add
the
it.
logs on max.
No, that's a good
The
question, because
main
sometimes you
point
can
is
think
that
about, I can
everything
make
gets
more my
normalized
models
to
wider or
and
deeper.
So
And
if you
deeper
multiply
seems to be
everything
working
by
better than
a
wider.
factor, You'll still get the same.
And we have some intuition for why that's the case, but still just
But then
intuition, not
this
really
step
like
then
formal
just
theory
makes
of why that's
everything
the
not overflow.
case. So it's
And
true
then
that
you
it's not
treat the
just adding
shifted
parameters, but it's
logic
adding
as
parameters in a
the
certain
I
way.
So then you
Okay.
implement something that
You're gonna make them deeper rather than wider.
would
But then
calculate
why
this
is deeper?
same.
So I just do like.
Right, because
shifted
deeper is like trying
logics
to
minus
learn
log of.
more features. Whereas wider, you're
actually,
trying
when I
to
just
learn more
started
complex
today,
features.
Don't call that like auto-completed for me. 'Cause I've already
You
like,
mean more features?
read the solution.
More different features, so if you think about an image, one
Right.
feature could be finding edges,
Yeah.
right? So you
Very
can have one layer that should identify edges, another one that is picking up on color, right? So, yeah, this is,
It's
I
not
mean,
auto-completed.
learn more complex
You can probably
feature
get a
learning,
little bit.
right? Or more of them,
Oh, okay.
and more of them seems to be more helpful.
But then
But
there should be like a GMP.
yeah, this is
log
very
and stuff.
empirical.
That's, GMP, that's, yeah. Yes, we will. Great. I was about to. Great mistake. Yeah. What's your model? What's your model? So you're gonna run into problems later because number of features that in your outputs are two. And so that means you can only sort of classify into two categories. So you actually might just 10. For the last output. Because what you'll want to get is a vector of 10 probabilities. Yeah, that's
So over here, do I change this to 10?
Right.
Because I changed it to 10 and then it threw an error for me. I don't know.
Right, so what's the output?
I have put 10.
Right, okay, but maybe something actually.
I don't know where it is find it. Here, yeah, I put
Right, okay,
10.
the output's 10, okay?
Yeah.
Let's go down again. Right, so yeah, I would say, let's go down. Right, so the shape of, right, this looks right, right? You get it.
Yeah, this one.
Yeah, that's good.
60%.
Yeah. So let's go down. Right.
Yeah.
Right, yeah.
Okay, what, yeah.
So-
So I wrote this for the this part.
Right.
It says write down the logs of those functions.
Yeah, I'm confused by why you have to.
I didn't, this was already there. I
It's
did.
already
Yeah, I did.
Optimize it. the size of the.
Oh, right, sorry, yeah.
It's like 64.
And
So-
it had two written over it.
Right, so it should be two, right, because this should be general, for any number of classes, right? So if you got it, it should be that. So it should work with two. So this is assuming that you have a total of class, so it's not for the.
Oh, okay, okay.
It's not for the general,
Okay.
right? If you're trying to.
Yeah, two work.
Right, then it's.
Okay, but it's not related to the 10, which.
Not really, this, the things that, yeah, I was just trying to see.
Okay.
So that's why.
Right.
Yeah.
Okay.
Let's go to that. Right, let's see, so. Right, so you haven't defined that yet, right? So if you look at the model I have there, you see that you have this like dense, and so the dense layer is the linear layer, so you bring some weights. Apply them to your.
All the
Right now you
corners are
can-
separate. Corners are separate objects.
Yeah.
I see,
So-
that's.
So I have to choose one of those.
Yeah, let's do. Right, so this will be like linear layer. So we do this. This next. X, right? So let's just do this. You see?
Yeah.
So these are going to be the kernel of the weights. You can check what the shapes of these things are. Right, it should be a matrix that converts your input size and your output size, right? But it will say, right now, yes.
Yeah, that's going to be used.
Yeah.
Now we have to
Purchased.
it's zero, is our first line.
That's
Maybe I'll come to this. Now we can try it. So, yeah. Check this. You're in it? It's 700.
Do you have any questions?
Oh, okay.
So it's like, yeah.
Yeah.
And this will be a matrix that will be applied in some piece of work, right? So we'll return something of 64.
So the matrix, what is the, it's 64 matrix. Have the size basically of 74.
Right, on the left, so we.
So 28 by 28. Yeah, 64. Okay.
Amazing. Well, no, sorry.
Okay.
So your input is with flat. So it's not a matrix. Or input is going to be.
Okay, so
So
you
it's 784
numbers.
matrix, right?
Yeah.
So when we apply this matrix, we'll get something after 64. We'll get 64.
Why do we have a one?
How do you account for that? Because you have a vector which is 64, has 64 components.
The output will have 64. Our images are classes, so our images have 784.
So that would be the vector, the input would be 784.
So when we apply this matrix, we'll get answers. So we're reducing the dimension.
Oh, so it's basically a 784 by 64.
Right, so it's
Okay.
projecting our
Yeah.
original set into a 64 space.
Okay, and that's the image which is then defined in this.
Yeah, we did that.
Okay.
So these are, and these are the values, sorry, random. These are the values,
784 by 64.
completely random right now. But the model will adjust it to
Yeah.
get the right answer.
And is this sort of the first one? Looks like it says 74 versus 64.
Well,
Or
this is the, so,
64 is now, okay. And but those are just random.
unfair, you see,
Oh, okay.
this just randomly.
Yeah.
But it definitely knows, right?
The other one, like C,
Now, my
We'll
matrix
get
has been
one of the second
76.
So that means those are not really randomized, they're basically part of the model.
this seed are random.
Interesting.
You can control
Yeah.
the generation, right?
Right,
So
but
they're
by
random.
choosing the key basically.
The one they're just
It generate how, which kind of random.
Randomization.
Yeah.
But it comes from like a distribution, but these are still random, but one will train and then they'll stop it.
Ah, okay.
But for now, they're random.
Whatever
And
is
then
that.
you generate, you basically set a 60.
Exactly. Once we apply them, so let's see. So this is applying the parameters to an example, right? So it doesn't work, right? But
Yeah.
Oh,
the shape is,
um,
what do you think the
So-
shape would be?
so it's 64, 2. so
What shape
that's-
is the outcome?
But the output, no, actually output is 64, one.
Well, because the batch size is 64 as well.
Oh, yeah,
And
we
the
have
output
64
is
vectors
68.
and yeah, okay, okay.
But what you want is an output of 10, right? Because you want the probability of each
Oh,
class.
Okay, so that's not how, but the
So
absolute run
we have to
So
modify.
you wanna have 64, 10, that
Then
is the
you
shape
have
is you.
64
Okay.
output.
But usually we have several layers.
One
So
output.
for now, we only have a linear, but let's add one node.
And then the 10.
So
is,
we add one node.
the output service
This is a very simple
numbers
model.
corresponding to abilities from each class.
And now we can add one more
I
layer.
didn't think it was, that's why it's 64.
Something correct.
Right, so, right, you can add another layer. So silo is nonlinear.
So it could be.
A very simple nonlinear function would be something like this, right? It's nonlinear, but it's still semi-linear, it's not linear.
I mean, in what regard?
Nonlinear is something, say,
So it's, so it changes the value that you get for the input, it would be nonlinear.
exactly.
So you can run an exponential.
Yeah, you go back to sine function, you go back to tan functions, but some of them seem to be more efficient than others.
Okay,
So these is one of the ones where it's like a smooth nonlinear, but not too nonlinear.
okay,
But if you piece many of them up together, then you can get something very non.
okay. Exactly. And now basically I will have to add after doing that, I will have to again, one of those that gets them.
But now it's
So,
and then it's direct.
What's happening?
is that?
Which would be the
Yeah,
the 10 feature.
Yeah,
that one would. So it's just sort of like the beginning, because I'm.
So then, that's
So you start with the 64, which are 28 to 28. So then you apply this.
Matrix mode.
Yeah.
So that's one there.
And I
Some-
don't know, but is sort of to estimate.
Right, so these matrix multiplications are set weights. That you want them to learn to pick up, right? So maybe you will learn that for once, there's certain pixels that have to have the value, right? So it will learn to pick up those things. So it's kind of what we call feature learning, right? Learning just the features of the feature. But for now, they're random, right? So the loss function would also have particular values. But right now, you're randomly initial. Right now, you're taking your data and randomly projecting it into the zero dimensional space, right?
Okay. But I mean, I looked at one of those, some of the samples, they all totally different.
Right.
So when you. Yeah, so I think.
Right, but when you change your input, your output will change as well, right? So the way we learn to react to data.
But somehow you have to compare it to the expected value. I mean, how do you adjust weights?
Right, with the loss function, right? So that's what you do. A training plan, you would pass in the inputs through this model.
Yeah.
And you'll get probability values for each class. So we'll be completely random, right?
Exactly.
And then the laws will tell you, you're completely wrong, move in this direction. And you'll use the gradient of the law to move in the right direction.
Right, but you still need something to put.
Second line.
Right, you have the true targets, right?
Oh, no, no, no.
You see that,
There we
that's what,
go.
that's what the comparison.
Okay, so there's a tool, so.
Right, so far we only have the architecture, right? The next step will be to do the loss function, where you actually use the true value. So if you go back to where it's not, so why not use the true value, right? So if you.
Yes, exactly. That's basically what. Oh, actually, so.
So you compute more than you need to, so then you throw out everything.
So why that?
Why that is the label, so the true value. So this is only one maybe. So it's 0 and 9 and 8. So you 64 examples.
Okay, so that's the sort of like.
Double amount,
Okay.
comparison between the predictions.
Okay, and the X then is. Here, so the images, yeah, and then that's what would be sort of like the side. Yeah, that's true outcome,
Yeah,
basically.
exactly.
And that's actually the main.
Yeah.
Because people are always like, how do you sort of like
Compare them.
compare them?
Yeah, exactly. That
So
would,
you
that would be
need,
the role.
yeah, so you basically are.
Yes.
Okay.
The locks of sometimes function in giving you the prediction. I'm having issues with the shape of the arrays. Do you have to reshape them?
So
For the predictions, so this is like after training, right after training.
Oh, so like in this one, when you like patch the network, that gives you
Yeah, so that one, yeah.
batch times 10,
Yeah.
So it's
right? But this is asking you just to get the maximum
Oh,
one.
oh, that's true.
So I think you use arguments. We'll just give you the.
Okay, so two things that I think are generally confusing people. So first of all, what is a silo? So what I said is that it's just a nonlinearity, right? That is very simple. So here you can see how it looks like, right? So this is a slightly nonlinear function, but it's not super nonlinear. Nonlinear with respect to the input, right? So here you basically go to a linear, it's like a piecewise linear, right? For x larger than 0. Then they have a small curvature,
And then later.
and then it goes to 0, right? So it's not very nonlinear, but if you piece many of these up, you can get a very nonlinear function, right? So that's the idea, that you can start with simple nonlinearities, combine them in ways that become very complex. But the main one is very simple. And the other thing that I think was confusing people is why are we batching our examples, right? Why do we get a batch of examples? And the idea of batching is that if I want to estimate my loss function, if I use the entire data set to estimate it, I will get one direction for the gradient, right? So in what direction should I move? Now, it's very useful to actually randomize this a little bit in case you're wrong, right? So this is what we call a stochastic gradient descent. So we're not just moving in one direction, but by batching randomly, so every time we call our loss function, we evaluate it in a random subset of the data to get a bit of like moving around, right? So that we're not just moving in one direction, but that we're randomizing the process a little bit so that if we were wrong, we're not totally wrong. We still have time to correct for it. So that's those two basic things that I think I didn't explain beforehand. So it makes sense that it got you confused.
What was what accuracy?
I mean, most.
78.
Okay, great.
It's fine, but like there are clearly more ones.
Talk about which
What do you like, I don't know if the syntax.
I guess,
Right. So you can
like,
see, yeah,
where some of the numbers are going, but I'm not sure, like,
function mobile apply, right?
choose any.
This one?
Or,
Exactly.
This is
like,
the prediction.
I also
Yeah,
don't know
so
where
this
this one is.
So you remember the shape was 6410, right?
Yeah.
Okay, there we go.
Okay, for all the images.
Smallest.
Yeah, text that.
You're getting two probabilities of the one. Maybe that way.
Well, you can, so like the more I got,
There's a find that, yeah, it's not just small, then you can read that number or just.
No, I mean, the sum of probabilities is not one.
oh, yeah, you did max. So like, if you go up to the.
And then what is this?
You see, I did softmax.
Like at the.
Those are the.
No, I have a dance at the end.
And so.
The output is a dance.
Basically, that's what.
Oh, you're calling it self then?
If you wanted to yourself.
Oh, interesting way.
I mean, this is how you.
Translate between numbers and.
Yeah.
Like images of numbers.
But this normalizes the output, so it's not so long.
There'd be a lot of sort of information content in that.
But then your
The
output,
neural network will do that for
what
you,
shape does it have?
but it has to sort of contain some information.
It's a 10.
And by whatever batch.
And you often need a lot of parameters.
Oh, I guess I should.
Complexity that is.
This is what I should do then. Oh, there we go.
That's, at least my interpretation. But,
That makes sense. Okay. I need to restart and pre-train everything. I guess.
My training was.
Do you get more of these for each layer that you do up here? Like, why
Yes,
did it?
each layer should correspond to.
I know, but.
Oh, you ran it several times, so you already converted?
No, I ran it, let me try running it again. You know what, let's recompile everything.
Because I think that it's saved on memory, so basically you already have the
side. The size. 28 by 28 is your input, and then four.
There we go, that
There you
looks,
go.
that looks.
Okay,
82%.
That's derivative.
Times
Here's there is no.
four.
That makes
For
more
the
sense.
sort of
Not continuous, right?
matrix
So
multiplication.
sometimes
You often
I
have
want
a
to take
bias,
derivative.
and
So let's
multiply
go.
some by some matrix.
You're predicting the position.
So you add a bias.
So if you take
This is
derivative.
wrong.
Time you
So
The nine?
Just a
Yeah.
huge number.
How many more values in your architecture you get?
So it's not-
Up and every couple of years.
But yeah, you know, maybe.
You have some not
Actually, the four is
non-linear
all-
distribution.
Whereas zeros are all, the first and second derivatives are all well defined. So sometimes it can be very handy if you want to take derivatives.
It's green.
In general, it doesn't.
Is
Yeah, I would go 5,000 steps.
Try it with like.
But it can be, I mean,
I
it's quite
prefer a gap.
So
This part is right.
that still will do equally well if you had.
Or yours have like
Like,
uh,
so it's
Try it for like.
very small difference.
9 on has 2, there we go, this makes more sense.
About jacks, because you,
Let's
Yeah,
let's
so
do the
Biases are
accuracy.
initialized
right?
zeros.
You're comparing
Instead,
the training run,
do
but starting with
92.
the same parameter.
92, yeah.
It's very
Adding
nice to
something.
do.
With just,
Going deeper doesn't.
Change the
I guess so, you just said.
whole thing is different.
Because you want to.
Yeah, it's
But
like.
your layers,
You don't-
you like 28, because that's the size of the input layer.
Yeah, and they get smaller, so let's try.
It's very small difference.
These are often
So I have 32 neurons.
random notions. Because you don't want. your
You only
matrix to be
32
all
neurons?
zero, otherwise you
Two
test
layer,
nothing. Do the number.
Wait, so you
want
have 32,
Sort of
So let me show you my
random,
architecture.
you have a much smaller.
transformation applied to
Yeah.
inputs so that the input information.
If you go
is
very
still
large,
present
you might,
in some
That's
noisy
true.
way as opposed to network. Then you learn
Yeah, I
how to
have,
transmute
32, 32, and then 10 in the other.
into sort of like noisy propagation into a more like efficient propagation.
Imagine if in this workshop, someone finds something
So that's
that
what the optimization
performs better than the.
Okay, like what's the leading, like, I got the same 85%.
You might even retry everything.
I just.
And I guess I didn't just, yeah, I didn't define probability. Am I supposed to do that?
Yeah, I think so you would just say,
Okay, this probably does make more sense.
the probability would be equal to.
Yeah, cause you're probably like
Model by
running a
5
second
grams
time,
of images.
so easy to-
So if you get the exponential.
So the GNP.argmax is sort of taking the max value
You get
of
value.
this
All that out is one.
So I got something that it says that it's a 9,
So instead
but I
of,
see
instead
it.
of argmax, so you don't want argmax, so you just want model that apply grams.
This is the 3, but it's a 5.
Oh, that's a hard one, yeah. But it looks
hard.
like a 5.
This one does say it's a 4.
Thank you.
It says it's a 2. I think MLP just like has a hard time.
Oh, yeah.
with this, right?
But the explanation was really great. Okay, now I actually have these.
Remember the first time I did this, it was with TensorFlow.
It was a pain. I've never done it.
So.
I think
let's look
it's-
at the
it's
training
fine,
questions,
right?
because
I would guess so.
I would have hoped that.
I think
it'd be
actually
better.
it's push nowadays.
So we go up.
It's
Probably.
nice that like all the popular architectures are coded up on.
Yeah.
So you don't have to do it yourself.
I think I should
Well,
change that.
I want you to
in Estimate.
return.
Like I have TensorFlow there, but
The last one.
probably gonna be first.
So you can go back, yeah.
So that's the last stuff.
But at least it shows that I know like.
So the
Background
predictability
stuff.
is key one, right?
Yes.
Now, what you have.
Yeah, like I
is
coded,
the
the first time I used a
any
transformer, I
values
could have it so. And then after a while.
Okay, so the question for Carol, it's beyond my expertise.
It's one, many bugs.
Yeah.
That will exponentiate and make sure.
Yeah, once you learn the ropes, there's no need.
So if you have your exponential, the values right now, like for mine.
Oh, I had the same issue because I wasn't normalizing the probabilities.
Okay.
So when you go to the architecture of your network,
Yeah.
make sure that the output of the network
Make sure.
is normalized. So this is the train.
Oh, yeah.
So where do you have your architecture all the way up, like in the
So you
second,
go from
second
minus
section?
to, so the Z goes from minus to one basic, so now there's.
That's what you define, yeah. So you need to, so the last layer needs to be normalized. So something like softmax would normalize your output. Okay. Mhm.
Exactly, if you apply this function.
I was missing that part as well.
That's why I want you to understand the log of this.
Perfect.
And then just, I would say just reinitialize your kernel or whatever and just run everything and it should just work.
Oh, this one got 90%.
Right, the Z is the opposite.
Sorry, so you're still behind.
How's it going?
92.
92.
What's that? Yeah, we have to sort out of it. Yeah.
This is, well, I can see.
Well,
that.
yeah.
I mean, it's still part of.
You have to modify it, right, to return 10-dimensional.
Oh, is it part of?
Oh, okay, no, so
So-
right now your model is
Yeah, that's.
but you want it to return 10, right? You want 10 probability values. If you want to add one more layer, type.
It's crazy.
I would normally go here and do a cosmology class.
Okay.
And then explain again, then.
Exactly.
You thought I was in my network since I came.
Yeah, try. It's just like 3 days.
That's not a lot.
I'll check later.
No,
How
but
big is
it's
the network?
like,
Yes,
it's like frustrating. Like, it's not like huge, but I have to do 6 of them.
and
Okay,
you'll have to pass in.
so hey,
So I'm doing
half a
like
month.
different network changes, subsets the output.
I was trying to
Yeah.
tell.
Mhm.
When like combined, they take like.
Oh, okay, okay.
So Silu seems to be.
Exactly, 10-dimensional representation. So actually, I think you've cheated, because there should be an error if it's not 10-dimensional. No, it's good, it's like.
What was the accuracy you were getting before?
The parameters.
95?
95? Oh,
95.
95? Yeah, 95. She's getting
Right, so
95.
now
What did you do to get 95?
I'm just like,
You're just cool, you're good at.
There you go. It's not mine.
It's like if I run this again, I'll get.
So one more.
Which is. Very widely.
It shouldn't, right? You change,
Oh,
oh,
it can.
are you changing your,
No, if I like just do nothing and moves again.
Then one would be then.
oh, because everything is on it, saved on.
It's all stochastic, right? So now I've got 91.
64.
So there's a bit of like,
Oh, but because you're changing your test, sorry, your validation set, right?
The other
Every time you run it?
do you? No, I think you just like, this
Because
happens.
you randomly sample the batch and then that's how you determine the.
Yeah, you change the batch order. So each time you try training, things change different.
The network should be okay.
So if you're like trying to
So you
optimize
change this,
the
right?
parameters, a lot of times you have
So now you're.
more clever optimization schemes.
Well, wait till you-
Like grab that, or you can just run it per setup.
Yeah, no, it's just funny. Yeah, that's. That's the first one?
That's the first one. Then, right.
Like what,
Yeah,
what
actually, I guess.
came up with when I started doing this, like. if
No, but
your
you can
network
try.
gets
I
stuck,
can-
I could try that.
you like lower the.
Everything.
It's like a learning schedule.
It's not showing me the abilities and I can't figure out why.
So now these.
Like,
10
there was
Is it in the last function?
Yeah, you can see it really.
It's the access.
Yeah. I don't know what the actual-
That's where you get.
The softmax, yeah.
Yeah, so
So then.
I think those are 0 to 1, but it may not.
Like, whoa, so like it got.
The access.
So you decrease the learning rate.
Here it's,
And it like immediately got.
Maybe.
I just.
Sorry, yeah, here's where.
So what this is doing is
I mean, I
uh,
can do that.
you're doing a finer step, right?
Yeah, basically.
So you're basically already converged according to the first.
Mine is actually.
Yeah, like this was already like, it took 15.
That part's
Oh.
actually fine.
Oh.
That's try reducing the.
I think,
Like, you know, clearly you get
labels
huge
here, right?
benefits you get.
For writing.
And does it really look different? Like the models, the first models look different? It's different like plateaus?
Oh, I mean, I haven't looked at the.
But yeah.
weight.
No, I mean, in terms of.
Yeah, performance, they definitely. Like,
So,
Right.
yeah, so that, the normalization.
So at the end, the actual value of anything, right?
yeah, what I'm doing, this is sort of analogous what we want to
Right.
minimize, which is delta chi squared. So like the loss function is like,
What's your model?
it's delta chi squared, but like.
Oh, well, sorry.
Square root to square.
It's the same, but I should put them to make sure they example.
So it's like a fancy, like,
Wait a minute.
But I was just wondering if you had a soft.
Oh, the delta Kuiper?
Yeah.
No, I just used the same that it showed, but I just.
I think that maybe an explanation is that if you have a suffix there at the end, then it makes everything sort of. One. And then.
Oh, okay. But they were taking 3 days. Was that in your laptop or in an Oh, okay.
Oh, and my desktop.
Okay.
Or doing stuff and essentially getting. Better.
Yeah, that's not something that I could do. Although Sometimes I could, but like, computer like correlation functions and stuff like that, I can't. I wouldn't be able to do it in the laptop. There's not a lot, no RAM.
So the shape of log ships is batch chroma classes, right? So if I do.
Here we go, hyperbolic. To delta chi squared, it does this thing.
For me,
If I do.
okay. All right, so that's 1 plus 2 delta chi squared.
Yeah. So like Evan. Come up with this. And tell me what's better.
Summing up.
Just the chi squared.
In terms of stability,
Yeah, like it's just the end.
I'm very
When you look
easy.
all delta chi squared.
Or
So the only way to like figure that out is.
So you want to first take the.
So.
when you said that that's specific to your problem.
Probably. Oh, yeah. Or like when you're trying to generate like data. vectors, like in
Something that I would wonder is kind of working things like this. This is supervised. It's really nice and unsupervised. Unsupervised.
Yeah, I don't.
So I just.
Yeah, I mean, they don't know how it works.
How it shows
Like, how do people go about
Small part of.
learning?
Yeah, now it, yeah, it's something, everything else standards, like. This part,
Yeah.
I think it's something to just do with dotting.
How are you defining this?
Yeah. So remember the Python is tab sensitive, so you want to have it. So that is.
Yeah, I have something to.
Okay.
Yeah.
Oh, I see. So then I just said probability equals.
Yeah.
Basically.
Also the output is, because it's softmax, the output is.
And now we're gonna try to input
Well, no, it's not.
random
so,
values for the.
In principle, what you would want to do is you would want to sum everything and divide
And
by
we
the sum.
try to evaluate the loss for.
To get the actual.
Because it's softmax.
So this model should be.
So the suffix does not look like, but it guarantees.
High value. Whereas this model is given a high value to class 1. So the loss should be high.
Yeah, so I just got rid of the, yeah, actually, that's.
So you have two classes, and here, the model, is a lot of weight
That's
for
fine.
class 0.
That's okay.
And the true value is class 0. So this model is good.
Oh, okay.
It's in the right.
Yeah.
So then the loss should be 0.
Right.
The one
Okay.
the class is 0.
Yeah. Right.
Now, this model is
There
given
you
for
go.
weight to class 1,
Okay.
but the true is 0. So the loss should be high. Yeah. Right, so,
Okay, so that is.
yeah, exactly. So in computation, it's good.
Oh, I see, okay. So it means. The
We'll pretend I'm.
See.
not loud. I know if I were to put it up
Yes,
right
no, I mean,
now.
that would be, oh, yeah, that's right. It's because of that. Oh, yeah, and that's basically what we. Yeah, something. Here and that.
You have more coverage that you predicted, correct? So
Right. I know.
these are randomly made by me, right?
Oh.
So it's an example. So if my model was predicting something like this,
Yeah.
I would want the loss to be zero, making the right prediction. Whereas if the model is predicting something like this, it's wrong, so it should have it. Just a test.
Okay, so it's not
Yeah,
related to
yeah,
sort of
well,
like
that one
our
is-
inputs.
Not really, no,
So,
this is a
okay.
completely random test.
Okay,
Yeah.
okay.
Yeah.
Yes, model that applies.
Let's put that
Yeah. Actually, no, look good.
Okay, that's.
So. It's like. Yeah.
So I would say this is a good time to take a 15-minute break if you want. If you want to keep working on it, I'll be around, so very happy to help out. But if you want to take a 15-minute break, it's a good time. So we can reconvene at, let's say, 3:20, and then we can talk about the generative model part, and we'll go over the tutorial next week. So yeah, if you want to take a break, please feel free to do so. We'll be back at 20:20.
Yeah, so the model. So all the jets. All
Like,
it's
can we
doing
get
is
some
it
good
defines
questions?
the model, images. So you go back to training. That's the training. So you see like.
Disappointing, huh?
That's how you call them on.
And
one
what
of
happens if you
the
add-
images. Yeah, creating set works.
I mean, the models are really pretty good, right? So this would be, those examples might be just very hard, 5% remaining. So it might be hard to improve beyond that.
I think that's like the for predictions.
100% accuracy.
Predictions of those lines.
Well, it depends, right? I mean, some of these are actually pretty ambiguous.
Well, sorry, true.
So there's a
I'm
limit
sorry.
to how well you can do something like that.
Well, sorry.
It's not the model's fault, it's the human's fault. But some of the, these are very clean, right? Like, yeah, they should have. Well, it could be a seven, right? The model is pretty sensible. It's not making a weird mistake, right? It's a mistake I would make as well. Okay,
So
the core
later
is
on,
that way. You're saying like to four,
So if you scroll down.
but often they're very sensible mistake.
So
But like this
next
could be
bit
fun,
here,
right? If you don't.
then this is like trying to plot just
Yeah.
image plus.
Makes reasonable
vector
mistakes.
Out in the models, you also want to generate that sometime in this array called probability. So I just set probability equal to just the raw stuff that's coming out of the model. It's just probability equals. No, not even soft. Just the logics. And then predictions would be the argmax of the probability of A. Yeah, so the maximum of each vector. So it should be argmax. Because you want
to select the number of features.
Index is the max.
Right.
To the maximum value.
Not really.
Okay.
So I would say want enough nonlinearity.
Don't
Right,
need to
so
take
here you
a
have
lot.
two. So you could do it.
That box
but,
up next.
I mean, this problem maybe is not that nonlinear, so it really depends on the problem.
Yeah, so instead of that, you should.
But
have
the number
logics.
of
Don't
like-
get
like-
the box.
you're too big, you see your model starts overfitting. So you can try, right? But maybe in this problem, not really, right? So if you wasn't seeing overfitting, so
Yeah.
in this problem, you might not actually see it. But if you go too large, you should see overfitting. So usually what I do in practice is I go large, see when it overfits. And then I know that I'm close to the model. Whereas if you start small, you don't know how much.
And how about the features? Yeah, if I increase the layers, it's really big problem.
Yeah.
How about the features?
Yeah, the same, right? We do more weights, so more free parameters. so you also-
Okay.
Usually it's that.
This is often.
I think it's one person.
Models.
Whereas you're wise, you're doing more linear.
Everything breaks. Yeah. Let's check.
Yeah. And also, in most cases, it seems that the features
All the way up to where you define the max.
200 times 6 times 15.
Yes.
But is there any reason for this?
Not really. I mean, it could be any number. But yeah, we usually like two to the power.
Yeah, right, so
Yeah.
in most cases, it looks like 64.
Always.
Yeah, I just want to check.
Yeah, I'm sure there's some historical reasons.
Then let's check your.
That's a.
Go down.
No, the log system either, right? But the argmax function takes as an argument, which acts as. Which.
To get some like good connections.
Yeah. Initially, I
This is
was,
the one that has
I
the.
don't know, something was going wrong and I was not able to see the predictions.
So then.
It was going from, it was just showing a very small number. But then
Right.
Peter said
That's
that
good.
I probably made a
Okay.
mistake in the value of the prediction.
Right.
So I had some step where I was taking the exponential, I removed it, now it seems like.
Right.
Oh, yeah.
Yeah, I guess that's just the prediction. I mean, it's predicting this to be 4, I would have thought it's very.
Oh, it looks like a 4 as well, right?
Yeah, no.
It's a reasonable mistake.
Yeah, yeah.
But it's true that your probability values seem very spike, like you go down.
Yeah, is there anything?
Well, you don't need to do the exponential of the sum.
Yeah, no, it's this one, for instance, yeah, it could be there. Yeah.
Okay, where is it complaining? To go down.
It's not a JX function, so.
Yeah, so if you go. I think I just guess what's happening, but I want to confirm from there. So if you go up there, it's. Sort of part. Well, let's check the passenger fees loss function. So let me double check that.
So it should be some.
So.
I think it's we get more.
Okay, but let's just take a argument. I. Yeah, but.
That's fine. That's one or just.
I mean, because the main difference here is.
How do we get the sum?
So what this thing is doing is it's actually computing this every number that you're doing. So it computes the value minus the log sum of the exponential. And then down here, it's you're multiplying this one out of it, which is 1 for the correct.
Yeah.
Exponentially to multiply that list of log sums. So it's throwing out all the most of the log sums, keeping something one that is. It's called something essentially positive. I think that might be what's happening.
Yeah, cool.
But basically, so, yeah, so this is a stuff. Basically a vector of a number of input image that I have. And then we want to subtract something.
Yeah, so the log of the sum of plus.
Yeah.
You're right.
Okay, there we go. Yep. Check that. Yes.
There. It's got exactly the same thing.
Oh, promising. Okay, so if you go down to this output, then. Yes, okay, good. Sorry.
Okay, so that already tells you that it's working.
Yeah, yeah, so let's give you the target square. And then when it completes, then you're ready to run the next step. To apply the last time. Yep. What's that? This thing? Yeah. What's that? Oh, you're training again?
Box looks like.
Yeah. Okay.
So.
Two Teslas.
Yeah, no, that's, wait, now it works, I don't know what I want to do. Change the thing that started working? Yes. Now it works.
Okay, good. Wait, yes, okay, good. Yeah.
Because we did have the same thing and mine was working and yours wasn't.
Yeah.
So why check the.
Thank you. I think it's that or. Yeah. Okay. So, yes, something after the yeah, you can send me an email or post it to other videos. Okay.
That's like training.
Oh, yeah, actually, yeah, actually over here. So what we define for somebody's different.
Right.
And then essentially it's not about it. We just use the sort of like we put on.
Right,
Sort of like basically log sum and then the exponential version.
That's just better. So I can see.
That's basically where it stopped. I've tried the other ones. Came up. So. Yeah.
Okay, the loss is going down. So this plotting the value of the loss at each step, right? So it's not very high, so the model should be wrong.
Yeah. What I'm seeing.
Sure. Right, so the value of the loss as training steps, right? So for each step, yeah, you're running it for a number of steps, right?
So that would basically be looking for the map or.
Right, exactly. So you minimize the steps. So the steps that you minimize that is trying to think, right?
Okay.
So you get a batch of 64 examples for each step, right? And you a different one.
Yeah.
So you can use 64 examples for your model. Get a loss value. So this is what the train step is doing, right? You're getting a loss.
Okay, yeah, that's sort of like.
And the optimizer is using that loss to be the gradient with respect to the parameters. And update the parameters.
Right.
So your number of steps is the number of times you're trying to update your parameters in the direction.
In the direction of the filters and then sort of like.
Yeah.
But
Well,
it stopped after a certain number of steps.
Yeah, it's just because you could keep going, right? And then you keep going down and sometimes it might stretch, or it might not,
Okay.
might keep going down, but you might be happy with the current, right? So you run it through a number of steps, this probably goes down, right? So it is. Yeah. It's good.
Okay. Okay, so that.
And now you can see what your prediction makes sense. The next step is about
What happens?
checking that your
Plug it in
predictions
3 beeps and
do
then
actually
shut
look
off.
good
Even though it says it.
on the test set, right? So now you will use the test set.
Yeah.
And you
Convinced
compute
that we can
things
use the
here
battery for it.
to make sure that they make Right, so the true values have a wide band, right? So you lay through. And now you have to call your model to get
No
the prediction.
It would have to.
So you want to pass those images through your model
For this one,
to see what your
I
model
liked
predicts.
it, because now I have an iPad.
Right, so your model takes images, right? And predicts 10 images. Okay. So your model prediction is probability, right? So your model predicts 10 values of probability, which one is the prediction?
So you get 10 probability values, one for each class, right? So which one is your model? Like you could have different ways to pick this, right? But it's probably the one with maximum probability.
Yeah.
You want to find from your model prediction, which one has the maximum. What class? From the 10 classes.
Yeah.
That's the maximum.
I guess that can.
Right, so you're predicting the 10-dimensional array,
Yeah.
which is probability of class 1, probability of class 2.
Oh, okay.
Numbers.
Yeah. So. Yeah, the loss function actually, right, which is things like, I mean, that's basically what we had before. I mean, that was actually almost the loss for is one of those 10 classes.
I guess.
And, so I should actually be able to.
Well, not in the loss function. Yeah, so the loss function is saying, given that the model is predicting this, and given the true value, how bad the mistakes.
It's so big.
It's quantifying mistakes. But right now, you just want to see the model predictions. So the loss function doesn't apply any role.
But didn't you use the loss function? Or so.
To find the right parameters in your model. But once you have your model fixed, so now you have learned that parameter.
Yes.
I want to see how good the predictions are last year.
And the predictions were right.
No, the predictions come from the model, right? So you go back to the loss function. It's the loss function, right? So it takes the model prediction and true value and assigns the mistakes. But these are already the model predictions. We're just converting them into probabilities, right? These are already.
Okay, so it's basically, that point, yeah,
It's
yeah.
quantifying mistakes.
That's, yeah, so that's what.
Right, so the loss function is this one, right?
Yeah.
So it's saying, these are all stations, these are the true value. So it's quantifying mistakes. But the model predictions come from the model, right? Not from the loss function.
Like I said, oh, yeah. Okay, I thought it does what it's saying, so.
Right, so POY,
Why?
so the model abstract. This is what the model. So then if we can recommend them into probability by different. But they don't mind them, like.
Yeah, okay.
Question, it doesn't matter, right? And now, this model predictions, I compare to the true value, the Y is the true value.
Why is it you're under hacker? Okay, I didn't.
So the last one is comparing predictions and true. Assigning a cost.
So that means when the sort of things try it, there's no why. And basically. I can see.
Right, you mean, so that's the reason, right? What's your number state?
Oh, it doesn't.
But if the prediction is wrong,
Using
then
that
the option
one.
can't. So the model predicts the same mistake.
Like keep type thing.
And that actually.
I can run.
That's.
Jackson.
That, remember that when you're taking.
It's
So this, we compare things. So I think that when you get confused is because we're doing that inside. No, we wouldn't have to do it. So the D is okay. D comes from. So the maximum entry will also be the maximum entry.
So just go into that and then. She's on top of that.
Right, so let's say maybe I could write something.
It's okay, because it was interest, so. Must be our house.
Yeah, that works. So your model function that outputs for some example.
They're pretty bad.
Yes, I'm using that.
This is your model.
Yes, yes.
Your English. So this is batch size. Right? And this is your shape, right? This is what your model is doing.
Right, yeah, that's basically what we do.
Now, the values of Z are between.
I mean.
So the model can predict any value. But we want to predict so we pass them to the subclass. I was listening to you. Sorry, let me, am I right?
So it is getting S320, so.
But these all comes from the model, the loss function plays no role here. The Z is kind of.
I've been there. Yeah, I guess that. But I don't see a lot.
Right, so you're using this loss function to optimize it. Q and Y comes from the model. So the loss function takes the output of the model, that's the true value,
Okay.
and you optimize that.
Right.
But once you're done optimizing, you already have probability values from your model.
Definitely good, sure.
So this is used to set the weights of this function, right? So this function has some weights. We optimize with the diffusion. Once you're done optimizing, now you're done. You have a set of weights that you can use the loss function. Now the loss is done. Now it's done. Now the model has the probability value.
Oh, okay, so you basically adjust
The weights.
Yeah.
Right.
So
We're
I mean,
using a lot.
in terms of cosmology, that's I think you're saying you're doing that would be saying that you would then set up like. And then basically.
Yeah, exactly.
Basically, the CIs from that one.
Exactly.
Okay, now I'm getting back. Not sure.
No, that makes sense. Yeah, but think about, yeah, what the boss is saying, and the mother saying. That's the right question, for sure. Okay, so we're gonna start with part 2. So I'm gonna, so we're gonna finish by 4:30, right? So we'll get wherever we get, and next week we can continue with the actual tutorial on. I keep saying that. Okay. Okay. Right, so I've seen some models working really well. The probability values looked actually very sensible, right? So sometimes you can confuse a 6 with a 0, which is sensible, right? Some people's zeros do look like 6s. So yeah, there were some very reasonable models out there. And so there were some very good questions about, yeah, how do we know how many layers do we have, or how wide those layers need to be? And the answer is we don't actually know, right? So there's a lot of experimentation here. So people were experimenting with making the layers wider or making them deeper. Okay. Usually depth is better than width because you're adding more non-linearities, whereas width, you're only doing more linear work, right? But again, it really depends on the problem. So hopefully one day we'll understand better why, why some things work better than others, but today that's not really the case. But okay, now we're going to be talking about generation. And I wanted to start with maybe what is the difference between discrimination and generation. So far what we've been doing is discriminating, right? So we were building models that look like the right-hand side here. So here you have images of cats and dogs, and you're trying to compute some probability of a class output given the image. So Y is the class, dog or cat, and you're trying to compute a probability that allows you to distinguish the two, right? That's what we call discriminative. But now we're going to be talking about something very different, which is generative models, where we're trying to actually generate from P of X. So we're going to be trying to generate samples of our images that belong to this probability distribution. So if you think about the conditional generative problem, sometimes we might want to condition our generative model. So unconditional means we're just sampling from P of X. So maybe we're sampling cats. Whereas conditional means we want to make sure we sample cats or dogs, right? So Y could be, again, cats or dogs. So P of X given Y, if I pass in dog, I will get images of dogs. If I pass in cats, I'll get images of cats. Now, these two models are actually related by Bayes' theorem, right? So I could write the probability of X given Y as the probability of P of Y given X. So in a way, they are related, but actually the problem looks very, very different. So if you want to distinguish cats and dogs, there are many shortcuts you can take, right? So the nose of a cat looks very different from the nose of a dog. So if you just focus on the nose, you probably have a very good discriminative model. The discriminative models can take shortcuts very easily. And sometimes that might be bad, right? Because, for instance, if you're trying to detect cows, if the model sees grass, you'll say, oh, cow. But it's only looking at the grass, right? So you put a car on grass, you'll be like, oh, cow. So these mistakes are very common, right? Because it can take shortcuts very easily. However, if you build a generative model, it has to generate the whole image. So it can't just focus on the nose, right? It has to learn what a cat looks like in general, right? And what a dog looks like. So actually what you can do to make more robust models is to build a generative model and then use Bayes' theorem to get a discriminative model, right? So this is the difference between likelihoods and posteriors. So actually, these models can't really cheat. They need to understand what a cow is and what grass is because they need to generate it, right? So this can be very useful in science, right? Where we actually care about models not taking shortcuts. But now we're going to be talking about these kind of models where we actually try to generate from probability distribution. What's the magic here? Well, what we're going to have in general is a parametric PDF. In the same way that we had a parametric function in the classifier, right? You had a model with dense layers, etc., that has some free parameters. We're going to have something very similar, but now it's going to be a probability distribution. Where we're going to have the data, right? P of x is the data, images, for instance, and some parameters that we want to optimize. So parametric PDF that we want to optimize. And the way we optimize it is very simple. If we can actually compute P of x for our parametric model, we can just maximize the likelihood of our training data. So make up the training samples as likely as possible. You can see it in this 2D example. So here we have the two-moon problem. Each point here is one training sample. It's just a two-dimensional problem, right? So each point has two values, x and y. What we're going to do is we're going to learn a continuous parametric PDF that we can evaluate at any point, so it's not continuous, and that we can sample from. So we're going to just maximize the likelihood of our training samples, right? So we're going to maximize the parameters of the PDF just to make the training data as likely as possible. So the principles are very, very simple. And the idea is that once we have our trained model, we can both generate novel samples from it, right? Like human faces. We can generate new ones that were not part of our training set. But we can also evaluate probabilities. So a well-calibrated model should be able to tell that this image has high probability in this data set, but a human with 3 legs is highly unlikely. Right? If you can evaluate probabilities, you should be able to tell these apart. Now, there's a lot of different names for generative models. So you might have heard some of these, so GANs, VAEs, normalizing flows, diffusion models. So these are all different flavors of generative models. And first, when you work on a project, it might be difficult to know which one should you choose. But today, I'm going to try to show you that there's a more general way of thinking about these models. And we're going to try and take that approach, and then we'll see that in some limits, these models show up. I won't talk about GANs because they're pretty much dead. They're very difficult to optimize. They're interesting. So GANs were probably the best generative models like 5 years ago, and the first generative models that got really, really good. So the first time that we could generate high-resolution human faces was through GANs. And the way they work is actually very interesting. So you have a neural network that's trying to generate your data, like human faces. And then you have another neural network that is like a critic. So it's trying to distinguish whether the image has been generated or whether it's a true image. And it's telling the other model, hey, I got you. This is generated. So it's kind of a game in which one model is trying to make the other one better. So it's a very interesting setup, right? But they're very difficult to optimize. So people don't like them very much these days, but they're actually very interesting. Right, the kind of models that we're going to be talking about will look like this. So you will have Bayes distribution. So this is let's think about a one-dimensional problem where your data distribution looks like this. So you have just like 2 modes of a Gaussian distribution, right, in 1D. So we're going to be building bridges between distributions. Our data distribution and some what we call Bayes distribution, which may or may not be very simple. So oftentimes it's just a Gaussian. So a very simple Bayes distribution. And now different models will make different assumptions. So first of all, about the Bayes distribution X naught. So is there any restriction on X naught? If we assume that X naught is Gaussian, that's what a diffusion model does. We'll see later how. Normalizing flows also assume that it doesn't have to be Gaussian, but you have to be able to evaluate the probability of X naught. So for a Gaussian, we know how to evaluate the probability of one example, right? For other distributions, we might not know. So you have to pick one that you can evaluate P of X naught. And we'll see later why this is the case. I'm just trying to show you what are the different modeling decisions that we're making here. Another question is whether this bridge between these distributions, or this mapping between distributions, is a stochastic or deterministic. So if it's a stochastic, you'll have something that resembles a stochastic differential equation. So the path that you're taking to go from one distribution to the other will be stochastic, like these red lines here, right? So this point here may belong to this area of the Bayes distribution or somewhere else. It will be stochastic. Whereas if this path is deterministic, be an ordinary differential equation, meaning this point here will always be transported to this point here in a deterministic way. And different models, again, make different assumptions. So normalizing flows are deterministic ODs, diffusion models tend to be stochastic SDs. The other thing to consider is how is this bridge constrained? For this path between distributions, what constraints do we have on it? So one could be that the reverse process, so going from X0 to X1 and X1 X0 has to be connected. So one has to be the inverse of the other. That's one constraint that we can set. And that's what normalizing flows does. A diffusion model would say, oh, the forward process is just adding Gaussian noise. One possible forward process, but it doesn't say anything about the reverse. Whereas we'll see another class of models, flow matching, where you assume you know one way forwards as well. But the basic idea is that we're going to be trying to find a mapping between our data distribution and a simpler distribution that we have more control over. So this simpler distribution, I know how to sample from, like a Gaussian, and I know how to evaluate the probabilities. This may or may not be used, the evaluation of probabilities. But the fact that I can sample from it is always very important, right? Because what we're going to be doing is we're going to be sampling from the simple distribution, and then we're going to learn the path to take it to our data distribution. But we're going to always start sampling from the base simpler distribution. So this is the basic framework, right? Building paths between two distributions, where one of them you control very well, the other is your data distribution. Yeah.
The distribution, say if you're trying to make images be a single image, it's like the distribution of values within, or is it all the images that...
Right, so this is all the images. So in this one-dimensional example, if I drew the actual samples, right, the training set, it will be points, yeah, right? That will be more likely to be around this area because it's where I have high probability. So here I'm showing the probability distribution. I'm not showing the actual samples. Whereas in images, each example will be one image with the number of pixels that it has. But in these one-dimensional examples, yeah, the training points will be dots here, there. Very unlikely to have something there. Does that make sense?
Yeah.
Any other questions about the general idea? Hopefully you'll get a bit more clear as we go. But we're going to start with what I think is the simplest of the generative models, which is normalizing flows, and it's still very, very useful. Because the basic idea is very simple. It relies on just change of variables. So if I sample from a Gaussian distribution with mean zero, standard deviation 1, so X is a sample from my Gaussian distribution, and now I transform my X with a random function, in this case, use a linear transformation, how does Y change? Distribution of Y, right? So I sample from X, from a Gaussian, apply a linear transformation, how is Y distributed now? Any guesses?
Another Gaussian, right? Because we use conservation of probability, so when the Jacobian is going to be K or something.
Exactly, that's the case. So we need to transform the Jacobian, right? Because probability mass has to be conserved. So what happens is that the probability of y is not going to be the probability of x. So you use the inverse of y to get to x, right? Which is, this is Gaussian, but you still have the Jacobian of the transformation, of the inverse transformation, right? And you can think about this as the conditional distribution function, right? So the CDF, cumulative distribution function, not conditional, have to be the same, right, for a particular value. So you can go through this, don't worry about it right now. You can go through it and see, convince yourself that this is true, that probability mass has to be conserved. So you get this change of variables rule of probability distributions, right? So for any probability distribution, if I apply any transformation G, so G does not need to be linear, it could be any arbitrary transformation. This is how P of X transforms into P of Y. So there's a basic idea from a normalizing flow is that we're going to sample from our simple base distribution that is going to be a Gaussian. And we're going to have a target distribution, that our data. And we're going to do is apply transformation G that takes our base simple distribution into our data distribution. Now, I've drawn a random one here, but actually, how do we know which one is the right transformation G? Well, we don't know in principle, so that's going to be a neural network that we're going to optimize, right? So we're going to find the function G that optimally transforms a Gaussian distribution into our target distribution. So the main idea is actually quite simple, meaning that we can sample from our base distribution and use the function G to transform it into our target distribution, right? And we can also evaluate probabilities because I can evaluate the probability of my base distribution and use the Jacobian to evaluate the probability of my target, right? So to sample, I'll sample from my base distribution that I know how to sample from, just apply the function, and I'll get a sample from my data. To evaluate probabilities, I'll use the Jacobian. So pretty simple. Actually, if you go back to 1934, people came up with this Box-Muller transform. So it's normalizing flows in 1934. They were matching a uniform distribution into a Gaussian. So this is a very simple way to sample from a Gaussian distribution. If you didn't know how to sample, so if you didn't have NumPy to sample for you, you could write down a transformation, which is actually this one here, that would take samples from a uniform distribution and give you samples from a Gaussian distribution. So this is one example that people actually came up with analytically. So obviously this is very hard to do in general. For Gaussian distributions is simpler, but it's very hard to come up with in general. So what we want is our normalizing flow to be trained to come up with the right function here, which will be an arbitrary function instead of a fixed one. Right, so this is another way to visualize what's happening here. So you have your base density, your Gaussian, and your target, X, and the function is mapping points into like probability densities into other probabilities. Right. Now, one thing that I haven't put too much emphasis on is the fact that this function f that we're using to transform the two samples has to be bijective, right? So it has to be invertible. Because if you remember what we had here, we go back to sample, we have to use the function. But actually to evaluate probabilities, we have to use the inverse function. So we need both. One to sample, the other one to evaluate probabilities. We need to move in both directions, right? Because our loss is going to be P of X. So to compute P of X, we need the inverse. To sample, we need the forwards. So the function has to be invertible. Now, this is actually not that simple to come up with invertible functions, right? So the multi-layer perceptron that you were working with, is it invertible? Like, can I get the inverse function to go from the output of the model to the input? Any guesses?
Obviously, it has to depend on the actual nonlinear functions that are used, right?
Right.
So if you use a ReLU function, then you lose all the information below 0, and there's no way to back it up.
Exactly, yeah. You're also adding things up, right? So if you add anything,
Right.
they're not invertible. So all the architectures I talked about today, none of them are invertible. So you can see how this is going to be a problem, right? So this is one of the issues with normalizing flows, is that coming up with invertible neural networks It's not straightforward. So there are tricks that we'll talk about, but it requires tricks, which makes them less flexible. So this is why normalizing flows are not the state of the art, but they're used for many things, and I'll highlight some of them because they're actually very, very useful. Okay, so we're going to be using this idea that we can have a loss function that is p of x, like maximize the likelihood of my data, by using the Jacobian of the inverse function, if it's invertible. And that's what allows us to evaluate probabilities, right? So in this way, we can sample from our data distribution, and we can also evaluate probabilities. So we have a generative model. Now, this will be a one-layer normalizing flow, but we can stack many of them, right? So instead of just one transformation, we can learn separate transformations to slowly get there, right? So you don't have to do it in one go, but you can do it in steps. So it'll be like layers. The idea is that because the functions have to be inversible, they're actually not that flexible. So if you stack many of them, it becomes a bit more flexible. So it's kind of a fix to something that is already not that great. But if you stack many of them, you can just adapt the probabilities, and yeah, you get to the function. But as I was saying, inversible functions are not that easy to come across, okay? So one that is used quite often is this idea of using splines. So this function y of x, you can learn it as a cubic spline, where the things that you're learning is the location of your splines and the values of these splines, right? Then you can compute the inverse. So this is one way to get normalizing flows working, is by predicting the knots of your splines. So you have a multi-layer perceptron that predicts the locations and the y values of your splines, the knots. Another way that's probably the most popular, or among the most popular, was called masked autoregressive flows. So you can make the predictions, p of x, for each feature. So if you have a 10-dimensional array, you just start from the first dimension. You can always make them dependent on the previous one. So the first one will be independent, but now the second feature will depend on the previous one. So this is what we call autoregressive, when there's a dependency on what you sampled previously. You can write this as a Gaussian with some mean and variance. So for each feature, you predict a mean and a variance. And now this is what the neural network will output. So for each cumulative feature, right? So whatever feature vector you're looking at, you predict a mean and a variance. So if you want to visualize it, what's happening, so if I have a n-dimensional x vector, for each, I'll start with x1, and I'll predict a mean and a variance, and I'll sample the value for, well, the other way around, right? We're going from z to x. So I'll start from z0, I'll predict a mean and a variance, and I'll get a sample for x, right, from this Gaussian distribution. And you can roll this out. And this is very easy to invert because now z is just the inverse of x, right? So by doing this autoregressive thing, we've made it invertible. So there's another trick. So you can see there's different tricks. You can use splines. You can use this autoregressive idea to turn functions that are not invertibles, like multi-layer perceptrons. So this is just a multi-layer perceptron, to turn them into actually invertible functions. But again, you've had to play some tricks here to be able to do this. So they don't turn out to be the most flexible generative models. They work mostly in low dimensions. So for images, for instance, high resolution images, usually you won't see a normalizing flow doing this. Where you see them used very often is in this area of simulation-based inference. So I work on cosmology, and we use them a lot in cosmology to learn posterior distributions. So in simulation-based inference, you have a problem like this, where you have some simulator that takes some input parameters. In cosmology is the overall composition of the universe. You run your simulator, and that gives you an observable, like the galaxy distribution, for instance. Or another example could be seismology, right? Where you have a fault line and some tectonic plates that are acting up, right? So you're seeing an earthquake, and you can simulate that forwards, right? So you have the plate characteristics, and you simulate forwards what the signal for the earthquake should be. But usually you want to go backwards, right? So you have some observation. It could be the galaxy clustering, or it could be your, I actually don't know exactly what they measure, vibrations of the tectonic plates, or whatever these people are measuring, and you want to understand what happened in the fault, right? So you want to go the other way around. So you want to get a posterior distribution for these input parameters so that you capture the uncertainty you have in them, right? So you want to know how certain I am that the composition of the universe is this one. And to model these probability distributions, we actually use normalizing flows a lot because these are pretty low dimensional. So we're talking about 10-ish parameters, no more than that, or maybe 20, 30, less than 1,000, let's say. And for that, normalizing flows are actually very, very useful. But still, they're very limited by this problem that they need to, the function has to be invertible, and most neural networks are not invertible. It's hard to come up with invertible functions. Any questions about normalizing flows before we move on? It makes sense? Cool. Right. So what people are thinking is that we've seen that we can make it one layer normalizing flow, or we can stack many of them. So if we stack infinite of them, we could think about them as a continuous transformation. So this is the idea that you could think about it as a continuous time thing. So if I play it, you could go from, in a continuous way, if you think about time going from 0 to 1, at time 0, you start from the Gaussian distribution, from your base distribution. At time 1, you morph into your data distribution in a continuous way. Now, why is this useful? First, because it allows you to think about this infinite stacking, but that's actually not the reason why they're most useful. You can, if you think about this infinite time, what you're doing is just thinking about this as an ODE. An ordinary differential equation, right? Where x0 is the base distribution, the Gaussian. At time 1 is your data distribution. So if I integrate this from 0 to 1, I can go from the base to the target, right? Now, this is what your neural network now is going to represent, which is a velocity as a function of time. So any time for a given xt is going to predict the velocity that it has to move. So this is representing the areas of the velocity field, right? How to move from one distribution to the other. So it'll give you this ODE. And this ODE is invertible, right? So now V could be any function, any neural network, and this is always invertible. If I integrate from 0 to 1 or 1 to 0, I can always go from time 1 to time 0 and vice versa, right? So now I can have an arbitrary neural network and still be invertible. So this is why continuous time, these are called continuous time normalizing flows, are very interesting because it allowed for any architecture like a convolutional neural network, multi-layer perceptron, without tricks. Now you get to an invertible function. Well, I guess you could call this a trick, but it's a neat one, right? The other ones were a bit more sneaky, where this is actually quite elegant, right? You have this infinite number of transformations, continuous time, and everything is invertible. Now, how do we do maximum likelihood estimation? Well, this velocity field basically gives you a continuity equation because the probability has to be normalized at any time. So you get this continuity equation for probability of xt. So now the derivative as function of time of the probability of xt will be given by the gradient of the velocity and the probability, right? So we can solve this to get p of x1. So how it looks like in practice, so this is a very common problem, right? Where you have 8 Gaussians spread out in a circle. So this is our data distribution that we want to sample from. So at sampling time, this is how it would look like. We will start from just 1 Gaussian, and we will learn a velocity field as a function of time that takes us to our data distribution. So the arrows, again, are representing the velocity field directions. And it's going from time 0 to time 1. 0 to 1. Now, to evaluate probabilities, we're actually going the other way. We're going from our data distribution back to the Gaussian, because these are the probabilities that we know how to evaluate, right? And using the continuity equation to get here. So if we write down the solution to this continuity equation, it would look like something like this, right? The log probability of your data would be the log probability of your base distribution, so the Gaussian, plus some integral of the Jacobian. Right? So you can compute it. Now, it's not very nice to compute. So this involves solving the ODE, like you can actually do it, but it's actually very time consuming. So to use it as a loss function is not great because you want to do this many, many times, right? During training time, you've taken 1,000 steps. So you'll have to do this 1,000 times. So this is not very convenient at all. So a lot of these other generative models are exactly doing very similar things as normalizing flows, a continuous time normalizing flows, but they're finding ways to avoid solving this interval at training time. So they're trying to get rid of the maximum likelihood loss because it's too annoying to compute, replacing it for something else, which is a proxy that will allow you to get the same data. But for that, you have to make some assumptions. Any questions about continuous time normalizing flows?
I think I have a more general question that is not only about flow matching and also normalizing flows. So I think in your examples, the initial distribution and the final distribution they have the same dimensionality, right?
That's right.
So, for example, when we're trying to generate a mock universe with galaxies and their properties based on, say, the cosmological parameters, you're apparently transforming, or you're trying to generate a much higher dimension space from a lower dimension space. So, I guess in this case, you're trying to, I guess, all of the galaxies actually live in a much lower dimensional Latent space. Is that true?
Well, I think we're conflating things here, right? Because let's think about the density fields.
Yeah.
So yeah, you have the cosmological parameters and the output. So if you run a simulation, this is your final density field. But actually, you're forgetting that you had the initial conditions, which was some initial density field that had the same dimensionality as the output, right?
Yes.
So actually, the cosmological parameters don't give you all the information. They give you all the information about the average universe, but not about this universe, right?
Right.
So here is something similar, right? So yeah, so when you're doing this, like here we have the 2D example. So the base distribution is also 2D, right? So we're sampling from a Gaussian that has 2 dimensions as well. Whereas when we have the 1-dimensional example here, we're sampling from a Gaussian that has 1 dimension, right? So it is true that the distribution you're sampling from always has the same dimensionality as your target distribution. So for most generative models, this is true. It's not true for VAEs. Variational autoencoders are doing something else. I'm not going to talk about this today, but yeah, those are the only ones that actually reduce the dimensionality and then upsample it again. But usually you always have the same dimensionality for output.
So I guess to follow up on that, what if I want to train a generative model with part of my purposes being trying to learn the underlying like low-dimensional Latent space? How am I going to do that?
Yeah, so actually you could do that with generative models. I mean, so what you're talking about is how do you, like representation learning is the idea of you want to learn a low-dimensional manifold where your data lives.
Yeah.
You can do that in many different ways. You can do that by forcing another model to be able to reconstruct your data, right? Given only the latent space information. Or you can do many different things. You can use generative models, that there are tricks. So you can use the generative model to decode the latent space, right? But yeah, that's not the main purpose of a generative model.
Sure.
A main purpose of a generative model is to sample from your data distribution and maybe to evaluate p-effects, depending on what you want to do, right? But learning a latent space is something you can do. You can use them to decode, very powerful decoders, right? But there's also other ways to learn representations that have nothing to do with generative models. Any other questions? Right, so we're going to talk in particular about flow matching, which is one way in which we can get rid of this issue of computing the loss is very expensive. So we can make computing the loss much cheaper. It's what we call conditional flow matching. So the idea is that we're going to fix the path. So we're going to assume that as a function of time, we're just linearly interpolating between x0 and x1. So remember, x0 is our simple base distribution, a Gaussian, X1 is our data distribution. So at t equals 0, we go back to X0. At t equal 1, we go back to X1. So there's like a linear interpolation between the two. So it may look like something like this, right? This is X1, it's two Gaussians. X0 is just one Gaussian. So we just linearly going from one to the other. Now, at generation time, we don't know X1, right? So we can't just follow the path. But we can marginalize over X1. So this would be the velocity field, ut of x, marginalized over X1. So what we know is the velocity field when we know where we're going, right? So if we go back to this picture, here, I know where I'm going, to X1, right? But at generation time, I don't know where I'm going. I don't have X1. I want to get X1. So at training time, yeah, I know my velocity field, but generation time, I don't, because I don't know X1. So I can try and marginalize over it. So this is what we're trying to do here. So I take the one I know at training time, marginalize over X1. Now, this is impossible, like it's intractable, right? It's too hard to evaluate. So we can't do that. However, what we can do is compute this loss function. So this is the velocity field for our known interpolants. It's just the derivative of this, very simple, right? X1 minus X0, very, very simple. So now we're going to approximate this with a neural network that doesn't know where it's going. So we're not going to input X1 here. So the neural network has to be able to approximate this velocity field without knowing X1. Now, this is a weird loss function, but it turns out that if you take the gradient respect to the neural network parameters, so the parameters of this velocity field, these are the same ones as the loss function that will have the true velocity field. Just because the gradients match, we can actually follow these gradients and end up at the right place. But yeah, the interesting thing here is that the velocity field does not know X1, but at training time, we do know X1. So we can actually evaluate this at training time. And then at sampling time, we can still sample because the learned velocity field does not depend on X1. So you can take a minute to digest that because it's not obvious, right? And this that I've written here as obvious, it's not obvious at all, right? So I'm just telling you, you can find the derivation in these papers, but yeah, it's not obvious. And it took people a long time to realize this. But now the model looks very simple, right? So we have this ODE. Okay, now I call it Z, but this is the same as X, right? We should call it X. We have a learned velocity field with the learned parameters being phi. So now we can sample from it by solving this very simple integral, right? So we just integrate from 0 to 1, the output of our velocity field, and we get samples from our data distribution. And again, we can still compute probabilities if we want to. But now something interesting is that, okay, we can sample and evaluate probabilities, but we don't need to evaluate probabilities for our loss function, right? So actually, it doesn't matter if I don't know how to evaluate the probability of my base distribution. So before, we were using a Gaussian always, because we can sample from a Gaussian and we can evaluate probabilities. And we needed the evaluated probabilities to compute the maximum likelihood loss function. But now, because our loss function is very different, right? It's just doing mean square error regression on the velocity field. We don't need p of x anymore. So if we're not interested in it, we can pick a base distribution that is not a Gaussian. So for instance, if you're trying to do super resolution, so you have a low resolution image and you want to get to a higher resolution image, right? There, you might want to X0 to be just your low resolution image because it's already very close to the high resolution image. And you don't care about the fact that you don't know how to evaluate p of X0 because you're not using it, right? So this can make flow matching models much more effective than, for instance, normalizing flows, because you're really matching the distributions that you're bridging are really very, very similar, which is not necessarily true for starting from a Gaussian into, if you think about turning white noise into an image, you have to learn a very nonlinear transformation, right? But if you have a low resolution image, it's actually very close to your target high resolution image, and you can take advantage of that. Right, so this is flow matching, and this is actually the model we'll be implementing. It's actually very simple, right? We're going to be learning a velocity field using mean square error loss. So this is what we're going to be implementing. However, you probably heard of diffusion models, right? So diffusion models were probably the state of the art until like, I don't know, last year or something. Well, they're still very used because flow matching and diffusion models are actually very similar. And I'll show you now how they're similar. So in a diffusion model, you also have like some sort of like infinite time here happening, where you have your data distribution at time 1, your base distribution at time 0. But your base distribution now is going to be Gaussian noise. So what we do is we fix the path going forwards as being adding Gaussian noise. So here we're adding Gaussian noise, more and more noise to our data, right? Until we remove all the information and we're left with pure noise. So this is fixed. Whereas in flow matching, it wasn't, right? I told you we could have picked any distribution. Here we're fixing it to be Gaussian. And then we're gonna learn a neural network that can take us the other way, right? So we're gonna learn to denoise this image, compute noise to the distribution. Then you can prop them, etc. But the idea is that the objective here is not maximum like we could, and it's not regressing a velocity field, it's denoising. So it's learning how much noise was added per pixel. So it's also mean square error loss, also a regression loss. It's not maximum likelihood. So it looks very similar to flow matching, but it's a slightly different objective, and you fixed this forward path to be adding Gaussian noise. So in the case of flow matching, we had this interpolant, this function of time, that was a linear, very simple. Here we have something similar, but with noise being added, Gaussian noise. And this is stuff that I was showing yesterday, right? So generating galaxy point clouds. So these diffusion models are very easy to adapt to other data modalities. So they can work with other things that are not images. So here we have point clouds, right? So we have galaxies, 3D positions that we want to generate from a simulation, and we can add noise to them so that we get noisy galaxy positions and learn a denoiser that doesn't need to be an image model. It can be, in this case, we're using a transformer or a point cloud model. So it's much more general. But it looks very similar to what we're doing to the images, right? We're adding noise and denoising. Yes, with point clouds, it can look quite different. Yeah, so the second tutorial is going to be about, with our favorite data set, still MNIST numbers, but now we're going to be trying to generate those numbers. So we're going to use flow matching to match these two distributions by the Gaussian. And then at different times, we'll see how it's transformed into the data distribution. So here I'm showing you the interpolant, right? So this is linearly interpolating from time 0 to time 1, from the Gaussian distribution to our data distribution. So yeah, given the time, this is what we'll actually be doing next week. But I wanted to finish with some stuff on large language models, right? Because I think if we're talking about generative AI today, we should probably mention large language models. And why are they generative models? So they look actually quite differently from diffusion models and flow matching, the stuff that I've been showing you. And it's still unclear why they seem to be working so differently. So people have been trying to do diffusion models for language for a long time, but it's actually been very hard to make them work as well as the current language models. So the current language models are autoregressive. So they're trained on next token prediction or next word prediction, right? So if you think about this sentence, the students at MIT are blank. You might have the options, right? Overcaffeinated, nerds, smart, athletic, right? So this is your vocabulary. So all the different options. Your model has to give probabilities to each one. So the same as your classifier, right? You want to output a probability for each of these ones, right? So it might look like something like this, right? So model has to learn what is the most likely outcome for the next word. But it's autoregressive in the sense that it's actually, at each time, it's generating the next word based on the previous ones it generated. It doesn't know how the diffusion model works. It's trying to generate the image at once. It's not trying to generate a pixel of the image based on the previous pixel. So it's still unclear why, for language, this seems to be working much better than, but I think people are making a lot of progress to make diffusion models work much better for language. The difference with language is that language is discrete, right? Whereas images are continuous. So that's been the challenge, how to build diffusion models that are actually discrete. But in theory, language models could be diffusion models. They're not right now. But this is how you pre-train them, right? By next word prediction. So you take all your text corpus from the internet, put blanks, and train them all for the next words. So it's a very simple pre-training strategy. Now, if you just pre-train like that, a language model, if you ask it something like, well, I think it might be, it's definitely too small from my eyes, it might work for you guys. But you're asking something like, write a poem about trees. And the model is just predicting the next word, right? So it's just rubbish, right? This is not very interesting. So this model is not very useful. So how do we encode the idea that we want language models to be helpful to humans in a loss function? That sounds really hard, right? Because it's not just about filling in blanks, right? That's not helpful. So how do we encode the idea of, please help me do what I want you to do, follow instructions into a loss function? So this is what we call reinforcement learning from human feedback, or RLHF. So this is why we call the previous task pre-training, right? Predicting the next token, because there's more training that is coming to make the models actually helpful. So the first step is you need a human to teach the model what is the desired output. So you have some examples where a human actually wrote a response. Then you're gonna use, again, a human to score the output of a model. So you kind of poke the model to give you different answers because it's probabilistic, right? So you can just call it many times, it'll give you different answers. And you have a human rank them. Be like, okay, this one was helpful, this one wasn't, etc. So yeah, this one was helpful, this one wasn't. And then you will train a model to score, like a human scoring, and use it as your reward function in reinforcement learning. So this is where your reward is, when is it helpful, when is it not helpful? And this is what actually makes the models much better. So this is the example I showed you previously before reinforcement learning with human feedback. And this is what happened after RLHF. So I don't know, that's pretty good to me, right? At least I would call this a poem, not the previous one, right? So models learn to follow instructions. So this is actually what makes ChatGPT so powerful and so useful. We had language models before, but they weren't actually following instructions, right? Next token prediction. That wasn't actually that useful. Now, some interesting developments is to get LLMs to reason, right? So if you've used like hot code or other coding agents, you see that they're giving you some reasoning of what they do, right? And there's some interesting things here actually where, so the human is asking for, it's not calling him the customer or the user, is the human. That's interesting. But they're kind of reasoning as they go. Right? Why do they do that? Well, what people have been showing is that if you look at the compute used for training and how good the model is, the more compute, the better the model is. Right? Now, if you look at the compute used when they're trying to get to an answer, you see the same trends. The more compute you use at test time, so when you ask a question, the better they get, right? So the more chances they have to iterate on their answer, the better they seem to be getting. That's the idea that this reasoning is actually helping the model get to a better answer. Another interesting recent development is to actually use verifiable rewards. So in reinforcement learning, actually, we were using human feedback, right? So there was a lot of humans in the loop, and that's very, very expensive. But actually, we know there are areas where the output is verifiable, like a calculator or code execution, playing a game, following instructions, things we can actually verify automatically, right? So it's actually what DeepSeek did, include a lot of this verifiable reinforcement learning, right? So post-training, so you train the model to predict the next token, and then you fine-tune it with these verifiable rewards. And that's actually very, very powerful. And then also you can build agents, right? So you can give the LLM an environment, so a set of things they can do, like, I don't know, householding, actually picking up things, apparently, or a puzzle or an environment where they can actually act, and then you can let them play around with things, right? So this is where we've seen a lot of impressive performance from like coding agents, right? That can actually write the code, run a test, make sure you get the right output. If it doesn't get the right output, it keep trying until it gets the right output, which is kind of how we work as well, right? So yeah, there's a lot of very fun developments in the area of LLMs. And again, the generative model paradigm is currently very different from what I've taught you, but things are shifting more towards that direction. So we'll see how it looks like in a few years' time. But yeah, I just want to end here with giving you some references of more introductory material. So this is a book I really like called Machine Learning, A Probabilistic Perspective by Kevin Murphy. And he actually has two now. So one more introductory, one is more advanced. So if you really like following a book that goes from down all the way to the bottom, that's a really nice one to follow. Then there is summer school. So the IFI summer school and this Pro AI summer school happen every year for undergrads and grad students. So these are great summer schools, in my opinion. There's the ML for Astro workshop, ICML, that will happen this year as well. And this is more a workshop where people working on astrophysics in particular and machine learning present their work. But if you're interested in just learning more about what people are doing with machine learning and astrophysics, it's also a great venue to just get to know what's going on and talk to people that are working in this space. And then there's some blog posts I really like also in this area. Sorry, just interesting reads, but actually there's Lilian Wang blog post is just in general very good. Same with the Standard AI. So you can look at other posts as well. But yeah, we have still some time for questions, so happy to take any questions.